you. My name is Hasitha Liyanage. I'm Director of Technology and Architecture at Cake. And I'm here to speak to you today about a topic that is very near and dear to my heart, application performance. So before we start, I'd like to tell you a little bit about why I accepted this particular topic, the fast segment. One of the reasons I chose to speak about this is that for the past 13 years, in one way or the other, I have been grappling with this problem, application performance. So before I joined Cake Labs, I happened to be in an industry that probably has the most stringent performance requirements in the world. Trading systems and high-frequency trading algorithms. I did that for 10 years. And as of late, for the past 3 years, I've been working on systems that use web-based technologies, but which are used by very demanding users. For example, right now I'm working on a point-of-sale system that are used by extremely experienced users who just have very high, fast reflexes. You just work very fast. And those applications has to be a lot faster than the average consumer mobile app. And in addition to that, this system is deployed in about 2,000 locations around the US, so that you have to think about the load as well. So some of the things that I have learned in the past 13 years, I want to share that experience with you. But unfortunately, or fortunately, this is not a talk about specific performance improvement techniques. Those techniques you can very easily enough find from a Google search, yeah? But what you really need to learn are the principles behind performance improvements. Even though I'm going to talk about a few techniques towards the end of my talk, this will mostly be about the principles. I think this is a big problem that we have with software engineering today, is that our minds are so cluttered with specific technology is the next latest cool thing that we are starting to forget about principles. Yeah, so let's start with the basics first. And we have a Q&A segment at the end, but just in case you have a very pressing question that you want to ask, feel free to raise your hand and ask. No problems there. Okay, starting from the basics. What is performance? A lot of you associate performance with speed, right? In fact, this segment is called fast. But in reality, it's a bit more subtle than that. What you call performance depends on what type of application that you're working on. There are two things to performance, latency and throughput. Latency is how long you keep the end user waiting. And that is something that ultimately translates, if you're doing a commercial business, it translates to sales. Throughput is how much load your technology stack and your hardware can handle. And that ultimately translates to cost in terms of business. So it really depends on what type of application that you're writing. So these two things, what you need to understand about is, think of a pipeline, your application as a pipeline. It can flow, let's say, 1,000 requests per second through that pipeline, and that is your throughput. But your latency is how long a request takes to go in from one end of the pipeline and come out the other end. So even if your system is handling 1,000 requests a second, if it takes 10 seconds for it to go in the other end, one end, and come out the other end, your system has high latency. So especially if your system has impatient end users waiting, or if it's a real-time mission-critical system like medicine, flight control, trading systems, this is your concern. If you have a cloud-based system that is catering to thousands or 100,000 users, and you need to handle it without shelling out a lot of cash on hardware, your concern is throughput. So as we go through this, think about your particular application domain and think about which of those two things or a combination of these two things apply to you as an engineer. Okay? So let's start with the first principle. Premature optimization is the root of all evil. Okay, what this is commonly understood to mean is that you should not worry about performance at the time you are designing and developing your application, because you will not know what your bottlenecks are until you have completed the application and subject it to a load test. Yeah, that's what is commonly understood to me. I am here to tell you this is wrong. This is completely dead, utterly wrong. This, in fact, I believe is the biggest misfortune that has befallen software performance, that engineers who are young, talented, but inexperienced misunderstanding this quote and parroting it every time somebody asks them to think about performance at the time of your requirements gathering, design, and engineering phases. In fact, this is the correct quote. And it's not Donald Nutt, it's Tony Hoare. I don't have time to go through these people, just look up who these people are. They are old school computer science and software engineering pioneers. The things that they have said, unlike today, the principles that they have said are timeless. No matter what your technology stack is, these things still apply. So here's the full quote. We should forget about small efficiencies. Say about 90% of the time, premature optimization is a root evil. He did not say thinking about performance during design and implementation is evil. What he meant was don't micro-optimize, which is to say that if you are writing a 10,000 line code application, what you need to really worry about in terms of performance is 300 lines, 3%. You need to identify those 300 and focus on those. So please, start thinking about performance at the time of requirements gathering and at the time of design itself. It is absolutely critical that you do this. So how do you find this 3%? Right? I just told you that you need to think about performance at the time of design, not after you start running the application. So without running the application, how would you know where the bottlenecks are? Here's how. How many of you know the Amdahl's law? Computer science graduates or undergraduates, if you are, you need to know this. Amdahl's law has a very common mathematical formulation, but the layman's understanding is this. The overall impact of improving a part of your code is limited by how often or how long that code runs. In other words, make the common case fast. Imagine a trip you're taking. 2-hour cab ride to the airport, half an hour jet plane ride to somewhere else, 2.5 total time. If you focus on your jet, make it even twice as fast, what you're getting out of that is a 15-minute improvement. Whereas if you spend some time improving your cab ride by even about 12%, you're still getting that same improvement, right? So you need to know where you focus. This is that 3% that Tony Hoare was talking about. So where do you find this? How do you know what part of the code is taking the most time if you still haven't written the code? For that, you need to know your hardware. Now this is something that modern software engineers are losing touch with, because all the hardware has now been very conveniently covered up in a sugar coating with virtual machines, the JVM if you're working on Java, the V8 engine or whatever engine of your choice if you're working with JavaScript. But please don't forget that you as engineers, when you write software, what you do is you are commanding a machine. And you have no right to command the machine if you don't understand it. Then you are just a technician. A technician is somebody who knows to turn the knobs, get the machine to work. You can open it up sometimes, you can replace components and repair it. But as an engineer, you are somebody who knows how the machine works, why it works, and if necessary, design and build a machine from ground up. That is what you guys need to be. Developers, coders, a dime a dozen, but engineers, they are a rare breed, very difficult to find, trust me. So you need to understand your hardware as well. If you're writing an application, let's say a mobile application, web application, you need to know the CPU architecture that you're working on, obviously the clock speed, number of cores. If you're running your application concurrently as threads, you need to know that. You need to know what is called an instruction set. I won't go into that right now. You especially need to understand a thing called the memory hierarchy. You know the memory hierarchy, I hope, right? The memory hierarchy exists because the faster a storage medium is, the more expensive it is. Not all the memory in your application can be fast as a CPU register. So at the lowest level, you have a little bit CPU register memory, level 1 cache, level 2 cache, memory, disk, and at the very top, cloud storage. So as you go up the memory hierarchy, your speed slows down. So when you're designing an application, you need to know what kind of data you have, how often do you need to access it, how often do you need to write it, and based on that, you have to decide which area of the memory hierarchy you are going to persist that data, right? And of course, the disk. Now, a common theme that I will return to as I speak is disk. There's a good reason for this. Your software basically runs at the speed of light, right? It's electrons flowing through semiconductors and conductors, but the moment you put a disk in, especially a non-nested SSD type disk, what you're introducing into the middle of that is a mechanical device. You have spinning magnetic platters and you have a head that's moving along it. And on one side and the other side, you have electrons moving at the speed of light. So your application, if it's a single-threaded application, it comes to a grinding halt the moment you have disk access in between. So I'll talk about in a bit how to mitigate that problem. You also need to know about the network. Network is actually lots over the disk. So the number of times you need to dip into the network, you need to reduce, and you need to understand the various quirks of a network. So I can tell you a story about this actually. About 10 years ago, I was working on a trading system, a component of the trading system that provides the market data into that trading system. And it had very stringent performance requirements. You had to handle about 30,000 requests a second. Each one had to be handled in the sub-microsecond range. It's very important. So what this component I was working on was doing was aggregating market data from about, let's say, 7-8 markets, putting them into a single message, and passing it into the trading system kernel so that it can make decisions. Everything was working fine. We tested it for about 30,000 messages. Can everybody in the back hear me? You guys can hear me, right? Okay, good. We did that. Everything was working fine until we added one extra market to that message, just about 20-30 bytes. Suddenly, without anything else, application performance just nosedived. And we went through all the code, reviewed all the code, and eliminated any probability of the problem being with the code. It was a complete mystery. So we found what the problem was. And to find this problem, you need to know something now. What happened was, the moment our message size exceeded a certain threshold, even by a few bytes, 1,600 bytes, this thing happened. So to solve this mystery, you needed to know something about the hardware. Can anybody guess what that number is? 1,600 bytes. This is the Ethernet frame size. So what happened was, the moment it exceeded 1,600 bytes, suddenly your message doesn't fit into a single Ethernet frame. It fragments. You are sending twice the number of frames to the network. That was the problem. So the solution was simply tweak our data structure so that it fits a single frame. So there are so many stories like this I can tell you that I've gathered from the last 10 years. Unfortunately, we don't have a lot of time, but during the Q&A or after this thing is finished, you can approach me and ask. Similarly, you need to understand the operating system because this is the gateway between your application and your hardware. Yeah, your application is not the only one that is running on your hardware. So if your application is a task switching application, sometimes while your application is trying to do something, your operating system might give precedence to another application. So those are also things that you need to worry about. Fortunately, not on the front-end side, on Android or say a web-based application, but especially if you're working on the back-end server side, this is something you need to know about. Right, so that is knowing your hardware. So back to this. If there's one thing that I want you to take away from this talk, if nothing else, it's this, the cost of hardware. Just look at this. Accessing some data from the level 1 cache from the CPU just takes 3 CPU cycles. Level 2 cache, 14 CPU cycles. Accessing something from RAM, about 20 times slower, but suddenly when you try to access something from the disk because of the reasons I told you before, it's about 250,000 times slower. If you go over to the network, it's even slower. So always keep this in mind when you try to look for bottlenecks. This is the first place. IO operations, this is exactly where you need to go to find your bottlenecks first. Remember that even displaying something on screen is an IO operation. Comparatively, doing mathematical calculations, those things blazingly fast on modern software, hardware. You don't have to worry about those. Right. So I told you that hardware access, IO access is extremely slow. So back in my day, when I say back in my day when I was a young programmer, the way processors or applications used to work was that they do all the calculations and then they come to a statement that has to access the database. You go to the database and your application is just stuck, just blocked, waiting for the data to come back, right? You did everything in about 10-30 microseconds and you spent 50 milliseconds, about a million times slower, waiting for somebody to send you data from a spinning magnetic platter. So that didn't work. So back in the day, what we used to do was delegate that to a separate thread, right? All the things, database access that we need to do, we put it as a request, send it to another thread. That thread does it, and once it's done, it sends us back the response. This is a form of delegation. So the first method of dealing with the IO problem or expensive operations problem was to introduce threads, or if you are in a web-based environment, this new technology called web workers. I think most of you may have heard of this. The other way is to delegate into a completely separate process. How many of you have heard of microservices? Okay, learn about microservices, not just in the context of performance or scaling, but it's a new architecture. Rather than writing your entire application as a giant monolith, you break it up into manageable chunks. That's another way. But the more recent way of doing this is what you call non-blocking I/O. I hope there are Node.js developers here as well. Yeah. Okay. Non-blocking I/O is not like getting another person to do. Let's say you're making tea, right? One of the blocking operations in making tea is you put water into the kettle, put it in there, and you have to wait, twiddling your thumbs until the water is boiled, right? That is your blocking. What you can do is you put the kettle, you continue doing the other things for making tea. I don't know how to make tea. I don't know. Maybe you do something with the tea and the milk and whatever. And you get a callback, which is the kettle whistling. And then you know certain steps that you need to do, take it out of the stove, pour, and all that. This is non-blocking I/O. You don't need a second person to do this for you. You set that operation, continue on its own, and you do your own thing. When it gives you a callback, you come and handle it. This is why Node.js, if you have learned about it, is a single-threaded application framework. It doesn't need any other threads because the vast majority of time that you spend on an application is not processing. It's waiting for I/O operations to complete. Disk, network, screen. Yeah. So that's another thing that we need to keep in mind when we're dealing with I/O operations. Right. Now that's done. All those things you have to do is before you write the application. But once you write the application, this is, I think, an area that everybody knows about. You need to load test your application and profile it. Yeah. And when you load test it, you need to know, you need to have a production-like data set. If your application is typically expected to deal with 100,000 users, you can't test it with 5 users and certify. It's not certified. You have to have a production-like data set, and you have to have some sort of automated tool or a script to generate the kind of requests that you expect from a production-like scenario, including spike days, and handle it. And you have various tools. I'm not going to list an exhaustive list of tools. Say if you're using Java, you might be using JMeter. If you're using a front-end web-based application, you might be using the browser's own profile. If you're on a Linux or a Solaris environment, you might be using dtrace. The most important thing here is to gather data from here, look at the function calls that have the most exhaustive use of resources or time consumption, start optimizing from there. In other words, Amdahl's law. Here's how you would go through. Let's say you have an application for argument's sake. On the front end, it may be an application running on WebView on Android. On the back end, it might be something that's running on Java, PHP, or Node.js, or anything like that, right? How you do this, how you look for application bottlenecks, is not just going here and there looking for it. You do it systematically. This is your stack, right? You start at the top. You have the user interface, client-side logic, client-side storage, client networking, the client operating system, and the network that connects your client and the server, the actual server, server logic, server storage, and server OS. A lot of you will first start looking for bottlenecks in your own code, right? But you also need to consider that you're also using at each of these layers libraries and a certain platform. So for example, if you can't find any problem in your UI, you need to look at whatever libraries you're using. You may be using jQuery, you may be using Angular, you may be using Swing, React, Qt, whatever. And if you don't find any problems there, you have to go to the platform itself. Maybe Chrome itself, maybe Android itself has certain quirks which you need to discover. Same with logic, same with storage. We recently had a problem, not recently, about 2-3 years ago, we had this problem with a Android application that is using WebView. Between page transitions, it was getting stuck. So there's nothing wrong with the code. We were looking for what the problem was. It just the entire screen freezes. What we found out was during each transition, we were loading some data from local storage. And if you know about local storage, it is blocking I/O. The entire screen, everything, including the scroll bar, will freeze until you retrieve the data. So what we had to do was we had to go for a slightly newer technology. If you have heard about it, we replaced that with IndexedDB. And it worked because that is asynchronous or non-blocking. So there are so many examples like that I can give you. Unfortunately, time doesn't permit me to. But you have to go through that process in all of these things, finding out what the problems are. And that's what you should be doing. So once you do that, here are some of the common performance bottlenecks that you will find. Again, repeating again, disk, file access, DB access, network, even on-screen operations. If you're writing a web-based application, you know what DOM manipulation is, right? The document object model. Those are I/O operations, even though it's a function call, because it manipulates something that is being displayed on the screen. Those are very slow. Another area that is commonly problematic, string manipulations, especially you're doing string concatenations, template generations. These take a lot of time. Loops and recursion. Any statement that you have inside a loop, figure out how much cost that a statement incurs, multiply it by the maximum number of times that that loop can execute, then you have the cost there. Object creation. This is a problem because modern programming languages are garbage collected. The more objects you create, the more of a burden you impose on your garbage collector. And remember, the garbage collector is using the same resources as your application. And any repetitive operation. There are certain things like reading configurations. All you need to do is read it once when your application starts up. You can keep it in memory. You don't have to keep reloading it again. So stuff like that you need to find. Let's actually get into some of the techniques. These are not specific techniques. What I have done is categorized all the techniques into about 6 or 7 basic categories. Caching is the mechanism by which if you have to do something again and again, retrieve something again and again, rather than doing that repeatedly, you cache the result somewhere and reuse it from there. Differing and chunking is this. Let's say you have a large, very long operation. Especially if you're on a single-threaded application, what you need to know is, as long as a single-threaded application is doing something, it is holding its breath. It's not breathing. So if you do it for a long time, everybody around it will think that the process is dead, drop connections, all these things happen. Especially in an environment like JavaScript, which is strictly single-threaded, right? So what you need to do, if you have a large data set to handle like this, you need to chunk it into smaller pieces and differ it with a little time interval in between. This is called differing. You can go and look it up. That's one type of thing. The other is delegation. Obviously, you can delegate it to another thread, another something like a web worker if you're on a web-based system. The other thing is, another area that is very slow is search. You used to use indexing, whether it's in the database or in memory. If you have a large data set, you need to have some kind of way to quickly access the data that you want without iterating through entire data set, which is going to take a long time. The other type is resource optimization. For example, things like minification, compression, so that you reduce the disk's footprint, you reduce the amount of data that you have to send through the network. And then finally, your choice of language, technology, and library. If your application is performance intensive, you do not go for the coolest, latest technology. You need to go for something a little bit low level. Sometimes instead of JavaScript, you may use Java. If that is not fast enough, you may use Golang. If that is not fast enough, you might even go to C and C++. Same with the frameworks that you use. Sometimes you will need to choose a very lightweight framework. But really, if you really think about it, the most important performance technique is this last one. You need to ask your requirement source, be they the client, be they your business analyst, how often a certain operation is performed, and if that performance, that operation gets delayed, how is it going to affect the end user? Without this, none of this matters. You're making assumptions. For recently, we had this application where there was a numeric keypad to enter data. And it had like a 300 millisecond delay. I thought, what's the big deal? 300 milliseconds. But then there was another area, user profile edit like area, which had a lag when you press the save button of about 5-6 seconds. So we were focusing on that 5-6 second thing. And then finally what we found out was these users are extremely experienced users. They tap this numeric keypad as reflexes. Tap, 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 and they are done. They go to the next order, tap, tap, tap. And this 300 milliseconds for them was infuriating because it was slowing them down. Whereas the profile edit, they were doing once every 2 months or so. So that's why you need to know when you're getting requirements, always ask how often does this operation run, how much your end user is depending on them. And finally, to 2 sets of specific, this is not an exhaustive list. I don't have all the time. What you can do is, like I told you, learn what these things mean and go and read about it. There's plenty of material on the internet for you to learn these. The virtual DOM. Like I told you, accessing the DOM on a browser is an I/O operation. What you really need to do is only change the parts of the screen that have changed. Don't re-render the whole thing over and over again. Virtual DOM or virtual DOM diffing is a technique that can do this. One of the pioneers is React.js, but I think the other frameworks like Angular, Ember, they're all coming into this. Then there's a technique called memoization, not to be confused with memorization. What memoization does is, if you have expensive operations, when that operation gets called repeatedly, this system checks whether the arguments that you provided into the function is the exact same. That means you have done that operation before. Why repeat it? Get it from a cache and give the results. That's memoization. And if you're working with browsers, you can delegate some of the work to web workers, so it's no longer single-threaded. Form of resource optimization is minification and compression. I think you know what these things are. In HTTP, you can use gzip for compression. There are plenty of minification libraries for you to use. And then, if your application is a rich mobile application or a web application, you will have so many assets: JavaScript, fonts, images, CSS. If you want to have HTTP requests to get each of these one at a time, that's going to slow things down. So what you really want to do is use an asset bundler. Maybe something like Webpack is very popular these days. You can use that to bundle all your JavaScript into a single file. Comes nicely in single request. That's on the client side, primarily. On the server side, if you're using a database, one thing you can do is you can use an in-memory key value storage like Redis. Most often used data sets, you can store it there. Or if you are using an interpreted language, you want to have something like the PHP op cache, if you're using PHP, or an equivalent thing in another language that you're using, so that you're not interpreting the same code over and over again each time you get a request. Or if you have a very I/O heavy and processor light application, you might consider Node.js because of non-blocking I/O. Or if you want to go really fast, you might choose a completely different technology stack like Golang or you can go to Java, or God forbid, if you want it to be even faster, you can go to C and C++. And of course, finally, database optimizations. You need to know about indexing. You need to know about what are the implications of having primary keys and foreign keys. Sometimes you have to go as far as denormalization. All these things are things that you need to learn about. Unfortunately, I don't have the time to explain all these things to you. You will have to do a well-placed Google search and find what these things are, right? But that said, sometimes, just sometimes, the solution needs to throw more hardware at it. Because in this day and age, hardware is cheap and developers are expensive. So it's up to you, once you have enough experience, to decide which way you want to go. This is a judgment call. I can't tell you what the right answer is. So that is my presentation. I hope I have managed to at least give you some insights about what I have learned over the past decade. I believe we are open for questions now.
So I invite Sandhu Nilanka. He's our GDG, one of our GDG organizers, to present you that.
Thank you so much.
Thank you very much.